Nothing beats. In this video, we are going to come up with the derivatives of inverse trigonometric functions. Specifically in this video, we will focus on the arctangent derivative, the arcsine derivative, and the arccosine derivative. Let's go. All right, so like I said, here's one of those derivatives. We're going to start by figuring out what is the derivative of the arctangent function, otherwise known, of course, as the tangent inverse function. So either way, whatever notation you prefer. So let's investigate. All right, just as a reminder, here is our graph of the arctangent function, the inverse function of the tangent function, and that's what our graph looks like. As we can recall, this function is nice and smooth, and it is defined for all real numbers x, so we should expect our derivative to also be defined for all real numbers x as well. Now, how are we going to go about doing this? Notice that as one of the properties of inverse functions, the composition of inverse functions, quote unquote, undoes them, in that, in this case, the tangent of the arctangent function is equal to x, and that's true for all real numbers x. And thus, if I went ahead and differentiated that equation right above, applying the process of implicit differentiation, go ahead and differentiate both sides of the equation with respect to x, as we can see in this statement right here. And when we do that, well, of course, the right-hand side, the derivative of x with respect to x is just 1. And then we get this other statement right down here below, in that, all right, well, we don't know what the derivative of that inner function, the arctangent of x, is, but by chain rule, we must differentiate that function with respect to x, and hence we get the derivative of the arctangent function with respect to x here, and then times the derivative of the outer function, which is the tangent function, which has a derivative of secant squared, evaluated at the inner function arctangent of x. From here, we can divide both sides by secant squared of arctangent of x to get that the derivative of the arctangent of x is the same as, well, 1 divided by secant squared of arctangent of x, but 1 divided by a secant squared is the same as cosine squared, so hence the derivative of the arctangent of x is equal to cosine squared of the arctangent of x. Now, that's true. That's the derivative of the arctangent function. However, we would like to simplify this result so that we don't have trigonometric function cosine of an inverse trigonometric function, the arctan. So to do this, remember that the arctangent of x is really a representation of an angle theta, such that the tangent of that angle theta is equal to x. Just think if I took the tangent of both sides of that equation right there. And thus, tangent of theta is x, and of course that is the same as x divided by 1. We can use this diagram right here below to help us understand what that is really saying. Remember that the tangent of theta is equal to x over 1, and so if you think of a right triangle like we have in this picture here, we have some angle theta such that the opposite side of the angle is x and the adjacent side of the angle is 1. And so we don't know the hypotenuse yet. Let's just call that length h. But remember, our goal is to find the cosine squared of this angle. And so in order to do that, we will need the length of the hypotenuse of this triangle. So just by Pythagorean theorem, right, we can see that 1 squared plus x squared is h squared. And so h is going to be the square root of 1 plus x squared, assuming that the length is positive here, not taking the negative root. And thus, like I just said, we get this result right down here. The length of that hypotenuse is the square root of x squared plus 1. And therefore, the cosine of the angle is 1 divided by the square root of x squared plus 1. So just go right back up here, right, and look at that triangle. The cosine of that angle theta, which is the adjacent value over the hypotenuse, 1 over h, but we just found that h was square root of 1 plus x squared. So, hence we get cosine theta is 1 divided by square root of x squared plus 1. Now remember, our whole point was to figure out the derivative of the arctangent function. We had found out that that derivative was equal to this boxed-in statement right there, cosine squared of the arctangent of x, and arctangent of x is just that angle such that it has formed the right triangle we saw previously. We just found out that cosine of the angle was 1 divided by the square root of x squared plus 1, and thus cosine squared of this angle would be, right here, 1 over square root of x squared plus 1 quantity squared. When I do that, I get 1 divided by just x squared plus 1, and there you go. That is the result that we want. And this shows that the derivative of the arctangent function is 1 divided by x squared plus 1. And as we hypothesized based on that graph we saw, notice that is defined everywhere for all real numbers x. So add it to the list. Here's our result that we just came up with. And you can imagine if we wanted to do something similar to find the derivatives of the arccosine function and the arcsine function, otherwise known as the inverse sine and cosine functions, of course. So, you can imagine doing that similar process, and in doing so, we would get that the derivative of the arccosine function, right down here, is -1 divided by the square root of 1 minus x squared, and the derivative of the inverse sine function is a +1 divided by square root of 1 minus x squared. And notice those are both only defined for values between -1 and 1 for x, not including the endpoints, of course, and that is all consistent with the domain of the cosine and sine inverse functions. So you can verify that on your own using a similar process. And so that gives us the 3 derivatives that we were interested in this video. And so what we'll do now is look at a couple of examples of just finding some derivatives. And in this first one here, we're asked to find the derivative with respect to x of the inverse tangent function of the square root of x. So remember what our result was that we just found. The derivative with respect to x of the inverse tangent function of x is 1 over 1 plus x squared. So if I use that result here, chain rule, we're going to have a 1 over 1 plus, well, not an x, but a square root of x squared, and then times the derivative with respect to x of the square root of x. And so obviously square root of x squared gives us an x, so we get a 1 over 1 plus an x, and then the derivative of root x is 1 over 2 root x. And so if we want, we'll just write this as 1 over 2 root x times a 1 plus x. And there you go. There's an example of a derivative involving the arctangent function. Let's do one more. Part B here, find another derivative. Let's find the derivative in this case with respect to w of the function arcsine of e to the 6w. Now, previously, as we had claimed, the derivative with respect to x of the arcsine or sine inverse function was 1 over the square root of 1 minus x squared, assuming, of course, that x is between -1 and 1. And so using that result, this is going to be a 1 divided by square root of 1 minus e to the 6w quantity squared. But then, of course, chain rule times the derivative with respect to w of e to the 6w. So differentiate, derivative of e to the 6w with respect to w is a 6e e to the 6w, and this is all being divided by the square root of 1 minus e to the 6w squared, but let's just write that as e to the 12w. And there you go, another derivative, this time involving the arcsine derivative. So that's it for this video. Came up and derived the derivative of the arctangent function, and the claim was do something similar and you can come up with the derivatives of the arccosine and arcsine functions. And then we did a couple of examples, of course. Now in the next video, we are going to go a little bit deeper and we are going to investigate the derivatives of the other trigonometric inverse functions, the arcsecant, the arccosecant, and the arccotangent. And until then, it's Math and Beats. I'm out of here.